This is a talk about functional inequality and transportation theory. And in particular, I would like to tell you about a transport map that I've constructed with Dan Mikulincer. This is all joint work with him, which we call the Brownian transport map. So let me start by motivating this talk with perhaps one of the more well-known functional inequalities, which are the Poincare inequalities. So what are Poincare inequalities? If we have some probability measure mu on Rn, or on Rd rather, we say that it satisfies a Poincare inequality with a constant C mu if for all functions which are nice enough, the variance of the function can be upper bounded by the expected gradient. And the constant C mu is the Poincare constant. And Poincare inequalities play an important role in many settings in probability and analysis, for example, for the mixing time, concentration of measure, and things like that. So given a particular measure, it's very much of interest to know whether it satisfies a Poincare inequality. One famous example of a measure that does satisfy Poincare inequality is a Gaussian measure. So here I denoted by gamma d. D for the dimension, this is the standard Gaussian measure on Rd. And indeed, it satisfies a Poincare inequality with the optimal constant C gamma d, which is equal to 1. And why is that? Is because if you take the function f to be linear, then you will get equality here in the Gaussian case with a constant 1. Okay, so at least we know that the Gaussian measure does satisfy the Poincare inequality. What about the Poincare inequalities for other measures? So the Gaussian is, of course, very special, being the Gaussian. For example, there are a lot of explicit formula that one could write. So proving the Poincare inequality for the Gaussian is not so difficult. But other measures that do not have all these special structures, it could be, of course, more difficult to prove the Poincare inequality. So the question that we'd like to think about is how to show Poincare inequalities for measures other than the Gaussian. Well, it's not like we expect to have a Poincare inequality for any measure, of course, but there are certain classes of measures where it might hold. So, for example, if mu is strongly low concave, meaning it's more low concave than the Gaussian. If it's low concave and has bounded support, so all of these are all measures which are somehow more concentrated than the Gaussian because either they're more low concave or because they're confined to a bounded support. So we might expect them too to satisfy a Poincare inequality, just like the Gaussian, because they're in a sense more concentrated than the Gaussian. Could also be maybe mixture of Gaussian, because we know the Gaussian satisfies Poincare inequality, so maybe mixture as well. Maybe bounded perturbations. In all these cases, we might expect to have Poincare inequalities, and indeed they hold. Of course, there are other examples. Okay, so how do we actually go about proving a Poincare inequality for any of these measures? So there are many methods, but I want to introduce to you one method, which is through transportation maps, that is also very applicable in other settings. We'll get to that in a moment. So let me show the basic computation, and this is really basically one computation that we'll have throughout the talk. So suppose we have a map T from Rd to Rd, which is Lipschitz with a constant L. And let's say that it transports gamma d into our target measure mu. Then I claim that mu satisfies the Poincare inequality with constant L squared. Okay, so why that? Let's look at the argument. So we look at the variance of mu and f. What does it mean for T to transport the Gaussian into mu? It means exactly this equality here. It means that if we take f and compose it with T, and we take the variance under the Gaussian, that would be the same as taking the variance under mu. So this equality just follows from the definition of a transport map. The next inequality would just apply the Gaussian Poincare inequality, which we saw before. So we said the constant was equal to 1. So we're looking at the gradient of this function, which is f composed with T. And then we do the chain rule. So the derivative of the map T comes out, but we assume that T is Lipschitz. So we upper bound it by L squared. And now we have the expected value of the gradient of f once we apply it composed with T with respect to the Gaussian, but again, using the fact that T transports the Gaussian into mu, we just get L squared times the expected value of mu with respect to mu of the gradient of f squared. So if we look at the left here and the right here, we see that the measure mu satisfies Poincare inequality with a constant L squared. So the idea is that if you have an Lipschitz map from the Gaussian to mu, you can transfer the Poincare inequality, which you know to hold true for the Gaussian, by paying a price L squared, which is where L is the extent to which the map T is Lipschitz. Now, the advantage of the transportation approach, it's not really special to Poincare inequality, as you might have noticed. Really, it could apply whenever you have something with a gradient. So let me just give you examples, but even without gradients, you have the parametric inequalities can be transferred using using transport map. Dimension-free phi Sobolev inequalities are just generalization of Poincare and Sobolev inequality. They can also be transported that way. You can look at higher order eigenvalues of weighted Laplacian associated with the measure mu, Q Poincare inequality, and many more. We will focus just on the Poincare inequality to make things concrete, but I just wanted to make the point that once you have an Lipschitz transport map from the Gaussian to mu, you basically get for free all the things that you know for the Gaussian, you get them automatically for mu. Now, it's not like we expect any transport map from the Gaussian to mu, even if mu is nice. We are not necessarily going to expect it to be Lipschitz. It makes sense that maybe we want to have some special structure on the map T. And in particular, let me start with optimal transport. So here's one way of looking at optimal transport. It's not exactly the Kantorovich formulation, but for our purposes, this is what we want to look at. So let's look at all the maps S which transport the Gaussian into mu. And let's look at the one which minimizes this quadratic distance. So here we have the map S. It maps the Gaussian into mu, and we're looking at the difference between X and S of X, where X is sampled according to the Gaussian. So the optimal transport map is the one which minimizes this quantity. This is the map coming from the Wasserstein distance. Okay, so this is a special map. It has some optimality properties because it satisfies this minimum. So maybe this map, if we look at the Gaussian as a source measure and some nice measure mu, the target measure, maybe this map T will be Lipschitz. So let's look at some examples. Let's say that mu is kappa low concave, with kappa greater than 0. Then there are different ways of showing this, for example, Bakri and Marie, that the Poincare constant of mu is going to be 1 over kappa. So if we follow the reasoning that we did before, we would expect that the optimal transport map to be 1 over square root of kappa Lipschitz. Because if you remember, the Poincare constant was the squared of the Lipschitz. So that's why we have a square root here. Okay, this is indeed true, and this follows from Caffarelli's contraction theorem. Okay, so that's good. How about another example? Let's say that mu is low concave, which this means that kappa is equal to 0, and the diameter of the support is bounded by some constant r. Then we do know, again, by various methods, that the Poincare constant of such a measure is on the order of r squared. So again, we would expect the optimal transport map to be on the order of r Lipschitz. But this is an open problem. Kolesnikov stated it in one of his papers as a problem when, to my knowledge, it's still not solved. Here's another example. Let's say that mu is a mixture of Gaussians, where so this nu is the mixing measure. So the diameter of its support is bounded by 1. That's not the support of the whole measure. This is the diameter of the mixing measure. That's it's supported by r. Then we know that the Poincare constant is e to the r squared. So again, we would expect the optimal transport map to be e to the r squared over 2 Lipschitz, but again, still an open problem. Okay, so the approach that we will take would be quite different. So rather than transporting the Gaussian measure from RD into our measure mu, we want to exploit something about the Gaussian. And the thing that we're going to exploit is the Gaussian is by nature a dimension-free type of measure, or infinite dimensional. And by that, I mean that you can view the Gaussian on RD as just a projection of the Wiener measure on the Wiener space. So what do I mean by that? So let's look at omega, which is the Wiener space. This is a set of all continuous functions from time 0 to time 1 mapping into RD. And let's take gamma infinity to be the Wiener measure. So this is the measure that if you sample from this space according to this measure, you just get a Brownian motion. And let's take mu again to be a measure on RD. Okay, now suppose we have the following map. Let's say we had a map from omega to omega, so from the Wiener space to itself, and I'm going to write it as, we have a sub t here because it's a function. So once you apply t to little omega, you just get a function from 0, 1 to rd. So that's why we have the sub t here. And let's say we have a property that once you project it at time 1, so its value at time 1 is distributed like mu. So just remember, for example, if we take t to be the identity map on the Wiener space, then at time 1, it will just be distributed like a Gaussian, standard Gaussian in RD. Because if you take the map, which is the identity, you just get Brownian motion. And Brownian motion at time 1 is just distributed like the standard Gaussian in RD. But now we're going to take this map T, which is not the identity, and we're going to look at such a map so that by time 1, it's distributed like mu, our measure of interest. So let's suppose, in addition, that T is a Lipschitz. So what does it mean? I mean that the derivative, okay, you have to define what do we mean by derivative here. So you need Molev calculus for that. But for now, let's just treat it formally. Let's say the derivative is bounded by L. Well, why would something like that be helpful? Because, again, because the Gaussian is an infinite dimensional measure, we know that the Poincare inequality holds also for the Wiener measure, the infinite dimensional Gaussian measure, with exactly the same constant that would hold true for the Gaussian measure on RD. So what does that mean? It means that if you have a function, a test function from omega to r, and you look at the variance under the Wiener measure, then you get a Poincare inequality because it's upper bounded with a constant 1 by the expected value under the Wiener measure of the gradient of f squared. And gradient, again, here means from the Molev. Okay, so how would we get a Poincare inequality from U? If we had a map T like that, well, we repeat the proof exactly as we did before. We look at the variance of mu under F. This is a measure on RD, of course, but that's the same as looking at the variance under the Wiener measure, where F is composed with a value of the map T at time 1. Now we apply the Poincare inequality for the Wiener measure. We do the chain rule again. We use the fact that the map is Lipschitz, and we get exactly what we want on the right-hand side. So what we see from here is that in order to apply this idea of transportation of functional inequalities from the Gaussian to other measures, because the Gaussian is infinite dimensional in nature, you do not have to start from the Gaussian on RD. We, in fact, can start from the Gaussian in infinite dimension, in particular. Good. So the question is, how can we leverage that? So first thing to try is, okay, how about we just try optimal transport maps on Wiener space? So there is a theory of optimal transport map due to Fayel and Ustunel. But in our setting, and there are a lot of interesting questions around that, but in our setting, it just reduces to optimal transport on RD. So we're not gaining anything because, as we said before, in all these measures that we're interested in, like low concave with bounded support and things like that, the question whether the optimal transport map is actually Lipschitz with the correct constant is an open problem. So going to Wiener space doesn't do anything for you. So what we do instead, we look at causal optimal transport. So this is a way of transporting measures, but in such a way that you also respect causality, meaning the filtration of the underlying Brownian motion. And I will explain a bit more about that. So what does that mean? So let's consider the following problem. Let's say we have a measure mu on RD, and we're trying to minimize the energy ut. So we think of ut as the function from time 0, 1 into RD. And this is like a drift that you add to the Brownian motion. So at time 1, omega 1 is distributed like a Gaussian, and you add to it this drift, and you require that it's going to be distributed like mu. Okay, so there are many u that will do the job for you, but the requirement is that we want to minimize the energy. So we're thinking about it as letting a Brownian motion run wild, but then we add a drift to it to steer it so that at time 1, it will be distributed like mu rather than like a Gaussian, and we want to minimize the cost. But the additional constraint that we have is that this process u is adapted to the filtration of the Brownian motion. Okay, so let's call u star to be the optimizer. And let's take the map x, which is just takes the Brownian motion and adds this optimal drift. This is our definition of the Brownian transport map. Because indeed at time 1, just by construction, x of 1 is distributed like mu, because we pick this particular drift. So the fact that it transports the Wiener measure into mu is just by construction. And now we would like to say more things about this map. And just as a side, what's the difference? Why is it called causal optimal transport? Because if you look at optimal transport on Wiener space, it would be the same problem, but you don't have the requirements of adaptedness. So by omitting it, that's you move into the realm of causal optimal transport. And exactly as we're going to show, doing that actually give you Lipschitz property that would not hold for, or at least we don't know, for optimal transport. So here the theorem, that we have the Brownian transport map such that at time one discrete like mu. So if mu is kappa concave, then we get that this map x1 is Lipschitz exactly with the correct constant. So here we recover the result of Caffarelli, but for the Brownian transport map instead of optimal transport. But now we can actually get new results that we don't know for optimal transport. So for example, if mu is low concave and the diameter of support of mu is bounded by r, then we get the correct behavior that the Lipschitz constant is upper bounded by r. Or maybe it's over r. I need to check. And here for the mixing too. So here it's not quite optimal because of the exponent in r squared, but it's almost the correct order. So the message here that by using transportation map, by leveraging the fact that the Gaussian is dimensional and using the causality, meaning the filtration of the underlying Brownian motion, we can prove things for the Brownian, for this map that we don't know for optimal transport and get the result. Because once we have this optimal, once we have the transport map, which is Lipschitz, as I said before, we can prove many other functional inequalities automatically by having this map. And indeed, we can improve on some results, for example, like log-Sobolev inequalities, which is known to hold for a mixture of Gaussian. We can actually improve on the constant in that log-Sobolev using our transport map. But I don't have so much time to get into the application. Let me mention another statement about the Poincare inequalities. This was already mentioned by Emmanuel, the KLS conjecture. So what is the KLS conjecture? If we look at all isotropic low concave, so again, kappa equals 0, then the conjecture that there is a dimension-free constant, which I denote here by CKLS, such that the measure mu satisfy that. So there's one constant, dimension-free, so that whenever mu is low concave and isotropic means mean 0 and covariance identity, we have a Poincare inequality. So given what we heard so far, you might say, okay, how would you go about proving something like that? Probably you should try to come up with some transport map which pushes the Gaussian into mu and it's CKLS Lipschitz. That would do that job. But something like that just cannot be true because, again, as we said before, if you have transport map, you can prove numerous other functional inequalities, not just Poincare. But those stronger inequalities are known to not be true for any isotropic low concave measure. There are some isotropic low concave measures for which stronger inequalities like that are just not true, where a transport map would give such inequalities for you because a transport map doesn't really care so much about the particular form of the functional inequality. So, okay, so from this perspective, it seems like you cannot have a transport map like that. But actually, there's a very beautiful result by Emmanuel that tells us that KLS would follow as soon as we show that the map T is Lipschitz, but not pointwise, but rather on average, in the sense that if we look at the expected value of the derivative squared with respect to the Gaussian, if that thing is bounded by this constant, then the Poincare inequality would follow. And the argument is quite simple. So now we have a new task, and the task is, can we come up with any transport map from the Gaussian, either in RD or from the Wiener measure, into mu, which is going to be Lipschitz with a dimension-free constant on average. So what is the connection between KLS and the Brownian transport map? Well, the current best bound on KLS due to Chen is almost a constant, but not quite. But then what we can show is that if you take mu to be isotropic and low concave, and you take again x1 to be the Brownian transport map between the Wiener measure into mu, then you get exactly the same order of Lipschitz, meaning using the Brownian transport map, you can recover the result of Chen. Now, I should say the proof that goes into proving that uses essentially the method of Chen. So it's not really a new proof. This is more of a new perspective on stochastic localization, which is the method used by Chen, developed originally by Onen Eldan, but it's a way of looking at stochastic localization as, in fact, a transportation map from the Wiener measure into mu. So this way, we have a new way of looking at this recent result about KLS, and the result is that we have a transport map from the Wiener measure to mu with a constant, which is Lipschitz on average, with a constant which is almost dimension free. If this was dimension free, we would get, of course, KLS. Let me say a little bit more about the Brownian transport map. I mean, up until now, I just told you that it minimizes a certain optimization problem, but in fact, you can write it explicitly as a solution to a stochastic differential equation. So what is it? Here is a stochastic differential equation. You take PT to be the heat semigroup, and you look at the equation, which is dxt, and here you have a term which is just a Brownian motion. Here we have this optimal drift that we talked about. So that is just a gradient of log of the heat semigroup at time 1 minus t applied to the relative densities between mu and the Gaussian at xt. So this is the optimal drift from the optimization problem that we've mentioned before. So the map X, if you just view it as a map which takes omega and spits out the solution to this equation, this map is what we call the Brownian transport map. So at time 1, for example, although maybe it's not evident from this equation, at time 1, it's distributed like. So just a little bit of a history about this process, where it's coming from. So it goes back all the way to Schrodinger in the context of large deviation. He wanted to know what is the most likely way in which an unlikely event will happen. And then it was formulated by Fulmer as something that has to do with entropy minimization. Then Lascelles showed that this process actually solved the causal optimal transport, meaning if you look at causal optimal transport, then you formulate it the way I did before, then this is actually the solution. He did even more generality than what I'm showing here. And Lehec showed how to use this process in the context of functional inequality. But the perspective of viewing it as a transportation map is really new. And using that approach, we can actually, as I said before, there are many other functional inequalities that can be proved once you have this transportation map. So let me just make some final remarks. So I stated the result about low concave with bounded support, but actually you can say more. You don't really need to be low concave. It's enough to be semi-low concave. And then we have a result which captures a balance between the size of the diameter of the support and to the extent to which the map is semi-low concave. There are many applications, as I mentioned before, once you have the strong Lipschitz property, meaning this is pointwise. But in the Lipschitz on average property, which we used for KLS, also has its own application to Stein kernels and new central limit theorems. There are many interesting questions still. What happened on the Wiener space itself? So you can also think about this problem as transporting a measure from the Wiener space, meaning the Wiener measure, into another measure on a Wiener space. I mean, we viewed mu as a measure on RD, but you can also view it as a measure on Wiener space. I don't have time to get into it. And there we also actually proved some interesting results where we showed that if you use a more stronger notion of Lipschitz, where your norm is now a norm respecting the structure of the Wiener space, then actually the Brownian transport map, there are examples which are not so trivial, where the Brownian, so it took some work to construct these examples, but in those examples, the Brownian transport map is not Lipschitz, while optimal transport is actually. So it's still not clear what the situation is there on Wiener space. And like I said, there are many interesting questions, including about optimal transport and other things. But I see that my time is up, so I will stop here. Thank you.